let me recall, we had the important notions of compactness. So when we had X row metric space and we had the notion of compact metric space, we had the notion of sequential metric space, sequential compact metric space, and then we had this complete and totally bounded metric space. And we found that all these are equivalent. Okay, so all these statements are equivalent. So therefore, to check compactness we could use any one of these arguments. Compactness by our definition is that every open cover has a finite subcover, and sequential compactness means every sequence has a convergent subsequence, and totally bounded we already seen. So now what I would like to look at before we go to some one or two quick examples is, suppose X row is a metric space, recall that suppose S is a subset of X. We take a part of the big universe and that part itself can be thought of as a universe within the universe, then S row becomes a metric space. Okay. This is the notion of, okay, this is called a subspace. Every subset in its own right, like you can have a vector space within a vector space, the same operations but now applied to a smaller, have a topological space within a topological space, same topological ideas. You can have a metric space within a metric space but the same metric, and so on and so forth. So this is the notion of a subspace. Now we can talk about S row being a compact metric space. What does that mean? If every open cover in S row for S has a finite subcover, because we are now talking about this small universe, everything is within that small universe. Every open cover within this universe must have a finite subcover, but any open set in the universe is the intersection of the set with the open set in the bigger universe. So this can be the same thing as, that is, every open cover for S in X row has a finite subcover. So what is meant by set? When we say a subset is compact, we mean whenever an open collection covers that set, it may not be exactly equal to S but covers that set, then it must have a finite collection. So therefore a subset S of a metric space X row is said to be compact subset if every open cover G for S in X row has a finite subcover. See, notice that we may have a vector space which is infinite dimensional, but it may have finite dimensional subspaces. Same way, the big universe may not be compact, but have subsets compact. Okay, so yes, S may be compact in X row without X row itself being compact. So that is the notion of compactness applied to subsets. First we define the compactness of the whole space, metric space. Now we are applying the notion of compactness to subspace. A subset is compact if whenever you can sweep it with open sets, you can also sweep it with finite number of them. Okay. Secondly, what is meant by the sub-metric space? Whenever you have metric space, you have the notion of sequence. So we can talk about S row is sequentially compact means every sequence in S row has a subsequence which converges. This, look at very simple examples in R first. That is the first thing. Then we will come back to more examples when we develop functionality a little bit more. Okay. So now let us look at a remark first. In particular, if you are looking at the real metric space, total boundedness is the same as bound. The boundedness and boundedness are same. So a set is compact if and only it is closed and bounded. So in the real line, so in R we know a set, a subset S is totally bounded if and only if it is bounded, and therefore we have, this is what is known as high number theorem, etc., etc. analysis. A subset S of R is compact if and only if it is closed and bounded. So that is a characterization of compact sets. In the real line, closedness and boundedness characterizes compact sets. In a general metric space, the boundedness has to be lifted out to total boundedness. Closeness and total boundedness characterize compact sets. Let us look at some simple examples now in R. Now that we have this weapon in our hands, we know what is meant by compactness on the real line. So let us look at some examples. First of all, we will see R itself is not a compact. R is not compact. Why? Not bounded. For fact in R, it has to be closed and bounded. R is closed because in a metric space the whole set is both closed and open, because complement is empty, empty set is open. Since the complement is open, this set is closed. So R is closed but fails to be bounded. Okay. So even though R is closed, it is not bounded. Okay. Hence now in the language of open sets, therefore there must be at least one open cover for R which cannot be reduced to a finite subcover. So therefore, hence there are many, but there must be at least G for R for example. So consider Gn to be the open interval minus n. Okay. So Gn is an open set for n equal to 1, 2, 3, etc. Now let G be the collection of all these Gn's. Then clearly G is an open cover for, if you take any real number, there will be sufficiently large n such that between minus n and plus n. Okay. Take the integer which is big and take, if it is positive, take the integer bigger than that and take minus n to n. If it is negative, take smaller than that and take minus n to n. So clearly it is a cover for R. Obviously you cannot find a finite subcover. This does not possess a finite subcover. Why it does not possess a subcover? If there was a subcover, then all the intervals being of this form, there is one fellow who is the largest interval in that, then that can cover only that large interval. Outside that nothing can be covered. So obviously this cannot possess a finite subcover. So therefore we have a cover for R which does not possess a finite subcover, and hence this is not a compact set. Now this proof immediately suggests that R2 with our usual this minus n can be thought of as the open ball of radius m about the point origin 0. Similarly in 2 dimension you take all disks of radius n about the point origin, contain a finite subcover. In 3 dimension we contain all the balls. Similarly in n dimension. So analogously in Rn, okay, for the time being I will just put L2 n R. Consider Gn is equal to Bn0. The 0 is the 0 vector. Okay. Bm0, then G equal to Gn n equal to 1, 2, etc. is an open cover having no finite subcover. And so L2 n R is not compact. And similarly L2nc is same argument. It is very easy. We will see that no non-linear space can be compact. Okay. So that is the first example. See, therefore, now we will see, even though the big universe is not compact, there are universes inside which are compact, there are subsets which are compact. So now consider the set S, the closed interval 0, 1 in R. Now it is closed and it is bounded, compact, because we have seen that any closed and bounded set in R is compact. Since S is closed and bounded, S must be compact. Like consider this interval, compact, yes or no? Is it closed? No, so therefore it cannot be compact. So not compact, though it is bounded, this is bounded, but not closed and hence not compact. What is a cover which we have? So Gn to be 1 over n 1, then Gn n equal to 1 2 is an open cover for S which has no finite subcover. Okay. Same argument as before, you can go only up some 1 over n, and between that 0 and 1 over n nothing will be covered. Similarly, S equal to 0 1 are not compact. They are bounded but not. Now instead of 0 1 I could have taken any a b, a and b are any two real numbers, a less than b. Okay, that is obvious. 0 1 is only the, everything is homeomorph 0 1. Okay. One more example I will give you. Let us consider all the numbers, all real numbers from 1 onwards. Okay, this is the set of all real numbers such that x is greater than or equal to. Is this set closed? Yes or no? It is closed because its complement is open, therefore it is closed. So this is closed now but not bounded, and therefore S is not compact. Okay. Again consider Gn to be, for example, minus 1 to n. Okay. Then Gn n equal to 1 2 etc. covers S but has no finite subcover. Okay. We will look at a little more examples later, but this is just to illustrate that when you are in R, in fact when you are in Rn, okay, that if you are in any finite dimensional vector space in which you put a metric, always closed and boundedness characterizes compactness. Whenever we lift ourselves to infinite spaces, then look at total boundedness instead of boundedness. Okay. So that is the notion of compactness. So we have so far seen completeness, separability. Dealing with compactness, we had the notion of total boundedness, also boundedness and total boundedness. So all these are linked by this theorem that in a metric space, compactness, sequentially compactness, complete total boundedness are all equivalent. I am now going to introduce one last notion in metric spaces, which is one last notion of type of sets. We have seen closed sets, open sets, we have seen compact sets, bounded set, totally bounded sets, sequentially compact sets, and so on and so forth. Now one more new. We also seen what is meant by dense sets. So this is somewhat connected to dense. So let's again recall. We have a metric space and we said a subset is dense if wherever you go you can find them. Okay, so that's what is meant by everywhere dense. Now I should have to be very careful. D, a subset of X, is said to be, I will not, but whenever I say dense, I mean everywhere dense. Dense in X, if wherever you go, you will find point. In other words, you take a point and draw any open ball around it or whatever radius, there will be a point of D sitting inside. Okay, so we'll put it in many ways. Okay, one, for every x in x row and for every epsilon positive, B epsilon x with any radius, any center, and with any radius, you take the fellow inside. In other words, everybody as closely as possible. Okay. That is, for every open ball B or X in X row, B or X intersection S is D is non-empty. This is what is being meant. Wherever you go, you will find it. You will find those fellows. This is what dense means. What is meant by somewhere dense? Means there is some place where whatever you do, they are there. What does that mean? There exists an open ball such that whatever smaller open ball you choose inside, there will be D points in that. So therefore, this means if there exists, here it was for every, there exists a BRX in X row such that for every BR1 X1 contained in BRX, BR1 X1 intersection S is non-empty. There is a space in which wherever you go you will find S elements. That is what is meant by somewhere dense. Okay, the traffic is somewhere dense right now. Maybe not in Bell Road, okay, but if you go to Majestic, it is always somewhere dense. It is always dense in Majestic. Okay. There, whatever small disk you take, you will find it there. Okay, so that's what it means. Somewhere it is dense. Now we are going to introduce the important notion which is called nowhere dense. What does it mean? Whichever angle you go, be some part where there is no traffic. Okay, that is what is meant by nowhere dense. That is, wherever you go, you can avoid them. So therefore, if for every Brx, wherever you go, there exists a Br1x1 in Brx such that Br1x1 intersection S is empty. So that is, you go anywhere, any typical place is open ball, you go anywhere, inside that there is a small patch Ys is there. You can avoid these pests and live peacefully. That portion will have no points of S. Wherever you go, there is a small patch which is free from these pests. Then it is called nowhere dense. So dense, somewhere dense, nowhere dense. Okay. So these nowhere dense sets, let me give you some examples. Let us take a single point on the real line. So let us take x rho to be the real line. Always first our basic examples will be this. Take S to be the single point 0. Obviously, wherever you go, you just avoid that point, right? So you take any interval. What is now? Whatever ball you take. What is a ball in real line? Open interval. So whatever open interval you take, if 0 is not there, you have already avoided it. If 0 is there, you can avoid it in a smaller portion. No problem at all. Okay, wherever you go, you can avoid. So it's not necessarily 0, it can be any A. Singletons are nowhere dense. You may take 2 points, that is also nowhere dense. If I take a finite number of points, that is also nowhere dense. Okay. So now we have S is nowhere dense. Similarly, I will write NWD. Similarly, any finite set is nowhere dense. But this does not mean any countably infinite set will be nowhere dense. We already know that there are dense. Cannot make any conclusions one way or the other about, but there are. Let me make this point and I will explain examples a little later. Okay, but there are one countably infinite sets which are dense, and also uncountably infinite sets which are nowhere dense. Okay. So the nowhere dense set has nothing to do with the size of the set, set theoretic size. Set theoretically this is small and this is big, but however this is nowhere dense, whereas that fellow is dense. Small and big are contextual concepts. Here in the topological concepts, nowhere dense is small, but that small does not mean countably infinite, uncountably infinite. So a set which is very big in set theoretic thing, uncountably infinite, can be very small from a topological notion, nowhere dense. So one has to be, it's only a question of small or big, beautiful or ugly is all in the beholder's eyes. Okay, so if you are a topologist, an uncountably infinite set also looks very small. It is nowhere dense. Okay, so one has to be very careful when one speaks. In fact, I used to have a teacher who always used to tell a joke that a student was asked, given an example, given a function, he was given a function and asked, is this function continuous? And the student was very sure that it was continuous, and then he said, absolutely sir, and he said, you are wrong, because the function was not absolutely continuous. There was another concept called absolutely continuous. So you got to be extremely careful, very precise in what you say when you do maths. When you say small, small in what sense? Okay. So there is the set theoretic cardinality small and big, topological density and nowhere density small, measure theoretically whether something is measured 0 or smaller measure than the other, theoretically how things compare. So there are different ideas of small and big based on the situation that you are dealing with. Okay, so now here this is a very fantastic example of Kant, who gave an example of a nowhere dense set which was uncountably infinite. And that example is itself is a source of several counter examples. What you thought was true will be proved untrue by that. Okay. So here, have you heard of this Cantor's ternary set? Yes? No? So this is actually from the Cantor's ternary set. It can be generalized further, but I will look at it a little more in detail later. So therefore, we have this notion of nowhere dense. It could be very confusing. Okay. Now therefore, topologically, what nowhere dense means, the elements of the set are somewhat sparsely distributed. Vaguely, I mean, intuitively we can think of that the elements of the set are sparsely distributed so that you can avoid them. Okay. That is the rough idea of the nowhere dense set. So therefore, now what we do is, what is we can build through this nowhere dense set. We have seen what we can build through open sets. Now we are trying, that is what led to notion of compactness and other things. Now we want to see what we can build. Whenever you get some special types of particles, you try to see how they combine and make something new. So we would like to now see what are all the things that we can use to build nowhere dense sets. Okay. Now let us say, look at these rational numbers, okay, Q. How many elements are countably infinite, but each individual is a nowhere dense set. So therefore, I am able to put a countable number of nowhere dense set and suddenly build a dense set. Okay. I have not count a nowhere dense set, but then all join together to become strong and become a set. So little drops make oceans. Okay, so that's the idea. So, but the thing is, suppose you have a finite number of nowhere dense sets, right, and put them together, what will you get? Still get only a nowhere dense set. For example, okay, let me put that, let me not even go into Q. Suppose S1, S2, Sn are nowhere dense sets in a metric space X row. So let S be the union of all these. I put them all together. So what I am trying to do is, what can I do using a finite number of nowhere dense sets. Okay. So finite number of sparsely distributed sets I am trying to. So now look at any BRX. So consider any BRX. Okay, any open ball in the metric space. Now S1 is nowhere dense. Inside this I have a open ball which avoids S1. So now I have got a B1, so there is a B1 which is contained in BRX such that BR1 X1 intersection S1 is empty because S1 is nowhere dense, right. Now I out the S1, I inside this because S2 is nowhere dense. Inside this there will be a smaller ball which will avoid S2 points also. So there exists BR2 X2 contained in BR1 X1 which is itself contained in etc. such that BR2 X2 intersection S2 is empty and obviously intersection S1 is also empty because already we have pushed S1 elements out. Now if I go on doing it after finite number of steps, the radius is going down because it is only finite not go to 0, which is provided all the, okay, after n steps we get B R n x n contained in BRX contained in such that BRN xn intersection S is empty or xj equal to empty for every j. Therefore, S is nowhere dense. We have completely avoided S. All points have been avoided. Why does this not work for infinite things? Because each time the radius is getting smaller and smaller, we are going to do it infinite number of times, there is a chance that this will become 0 and you won't get an open ball. Okay. So therefore, when you put a finite number of nowhere dense sets, you are not getting anything new, you are still getting only an nowhere dense. Okay. So therefore, finite union of nowhere dense sets is nowhere dense. And therefore, we now look at what we can get when we put the next level of union. After finite it is countably infinite. If we now put a countably infinite union, so now I am going to look at countably infinite union of nowhere dense sets. If I now take a countably infinite union of nowhere dense sets, the rational numbers already tell you are going to go out of the nowhere dense separalim. You may even get a dense set. So therefore, when we put a countably infinite number of nowhere dense sets, there is a chance that new. So therefore, now we see what is it that we get what by putting together finite or countable. If you now put finite or countably infinite number of nowhere dense sets and you build something, such pieces are called the first level of my construction. They are called first category sets. Okay, this is the first time the notion of category is introduced. Okay, so now sets now obviously the empty set is nowhere dense. Wherever you go, you can avoid it. So therefore, you can think of a countable union of nowhere dense, finite union of nowhere dense, also as a countable union of nowhere denses by putting number of empty sets together. Okay. So therefore, our main aim is countable. Okay. So a subset metric space X row is said to be of if as countable. When I say countable, countably infinite, finite or countably infinite. Countable or nowhere denses. Then it is said to be of first category. For example, the rational numbers are of first category. And any nowhere dense set is automatically first category because it is a finite unit itself. Okay. So therefore, any finite set, any nowhere dense set is first category. So what we are saying is nowhere denses and their descendants are all called first category fellows. They have the same gotra, whatever it is called. In any nowhere dense is first category. Q in the metric space R is of first category. First category, but not nowhere dense. Because it is a dense set, but it is the union of individual members. Each individual member is nowhere dense set. So there is a countably infinite union of nowhere dense sets, and therefore it is first category. Okay. Now the question is, are there anything other than this, or everybody is first category only? Okay. You put enough number of spars and fill up the whole space. So the question is, let us put it this way. Question, is the set of irrationals, say I, we will denote it by, of first category? We will look at that question. We will see that it is not. And therefore, there are different types of fellows. They will be called second category. Okay. But at the moment, we do not know whether there are second category sets at all. Right. So now, suppose this is true. Suppose I is of first category. What does that mean? I is the union of an, where an are nowhere dense sets, because countable union of nowhere dense sets. But we also know Q is the union of nowhere dense sets, right? So, is a countable union, this is a countable union, I put them both together, what will I get? Again a countable union of nowhere dense set. Therefore, I union Q is the countable union of nowhere dense sets. But I union Q is all of R. We have taken the rationals and therefore R is of first category. If I were to be first category, then that forces the real numbers to be of first category. And they are put an end to it and said the real numbers cannot be of first category. And in fact, he showed that no complete metric space can be of first category. Okay. So that's the famous Bayer's category theorem, which has phenomenal number of applications. One of the finest theorems in analysis, which has given rise to many useful theorems in analysis. So Bayer's category theorem. It has very many general formats, but I am going to state only this. Okay. A complete metric space cannot be of first category. And therefore, we have to introduce the name that whenever something is not first category, it is called second category. That is, what does that mean? That is, a complete metric space cannot be expressed as a countable union of nowhere dense sets. That is why the rational numbers had that defect. The limits were missing. Because in other words, what you say is, don't be over ambitious. You are trying to build a complete knowledge set by using sparse knowledge sets. That is not possible. Okay. So you can reach some level, you could even get to dense level, but you could not reach the whole level of nature. Okay. So there will be some deficiency, because that genetic deficiency is there to start with. Every one of them is a sparse set, but somehow that genetic deficiency will carry through, and you will see that you will not fully grow. Okay, that you will not be a complete set. You will not be a complete metric space. So this is a very fundamental theorem in topology, in metric space theory. It gives rise to many results. What I want to do is now, I will just put another remark. There is another equivalent way of looking at nowhere dense sets. Okay. What I give is the classical way of defining nowhere dense set, but I like that definition because it tells what is meant by nowhere dense. Wherever you go, you can avoid it. That is a very simple, intuitive definition. But we have a set S is nowhere dense if and only if you look at the closure and look at its interior, that should be empty. The closure should not have any interior. There are no interior points in the closure. Then we say it becomes a nowhere. That's another way of looking at it. To prove theorem, sometimes this is useful, but to understand the definition, this is useful. Okay. The interior of the closure must be empty. For the moment, I will hold the proof of Bayer's category theorem. It is very simple, basic application of Cantor's intersection theorem. Okay. You construct a sequence of closed sets whose diameter is going down to 0, and you get a point, and you say that if the metric space was expressible as a closed union, then I will produce a point which is outside that union, which is coming out of this intersection, and that will lead to a contradiction. So basic idea is, so basically Bayer's theorem is Cantor's intersection property stated in a different language. Remember Cantor's intersection property in a complete metric space, if sequence of closed sets whose diameter is, which are going down and whose diameter goes down to 0, the intersection is a singleton. So what we do is, suppose X is complete and X is the union of AN nowhere dense. Suppose it is possible. Suppose the theorem is false. Then you construct a sequence of these closed sets and get a point at their intersection and show that this point must be outside X. Is in X and it will be outside X, and that will lead to a contradiction. So that is the rough idea of, it is basically therefore Cantor's intersection theorem redone in a different language. So these are all the fundamental ideas that I will be using, one would need to really start doing a functional analysis. The notion of completeness, open sets, closed sets, completeness. The open sets, closed sets ideas are all topological, basic fundamental topological ideas. Then the types of sets that you would consider, compact, bounded, totally bounded. Then the ideas of separability, dense sets, nowhere dense sets, category. All these are the languages and the basic tools that one needs to do the functional analysis, and then you will see many interesting things that come out. What I will do now is, probably I will not prove the, there are some very interesting funny things one can prove using, not funny things, very intuitively non-clear things which one can prove using Bayer's theorem. I am going to give one simple instance. Okay, it just suddenly occurred to me that I should do that. Okay. Just the things are, you know that analysis is easier in sometimes complex variables than in real variables, because in complex analysis, if in a domain, if you have one different derivative, all derivatives automatically come into the picture. An analytic function has all the derivatives, whereas in the real numbers you got to struggle. Okay. So let us look at it in the complex. What is meant by an entire function? You know what is meant by an entire function? The function which is analytic everywhere in the entire complex plane. That is why the word entire. It is analytic in the entire complex plane. That means it possesses a derivative at every point, complex plane. Okay. So now suppose I have a polynomial. Okay. Say of degree 2. Let us say first of degree 1. Polynomial of degree 1. Okay. Then if you look at the second derivative, what is that? For all, we take a polynomial of degree 1, the second derivative is 0 at all the points. Similarly, if you take a polynomial of degree n, polynomial of degree n, a0 plus a1z plus an z to the power of n, then the n plus 1th derivative is 0 for, right. So if we have a polynomial, then there is some derivative, some order derivative which vanishes at all the points, right. Conversely, if we have a function, analytic function, which is such that some order derivative vanishes at all the points, then that must be a polynomial. Okay. So this is a very fundamental properties of polynomial. So therefore, what we have is, if f of that is an entire function, let me put it entire only, make things such that there exists a non-negative integer k such that if the kth derivative is equal to 0 for every z in C, then the conclusion is f of z must be a polynomial. So this is the characterization of polynomials. How is a polynomial characterized? The fact there is some order, the derivative of the order must be 0 for all z. Now suppose I have a function where I don't know whether the same order derivative vanishes at all points. I know that every point some derivative vanishes. This point the 4th derivative vanishes, that point 8th derivative vanishes, that point 12th derivative vanishes. I don't know that the same order derivative, k order derivative vanishes at all points, but at every point some order derivative vanishes. Will it still be a polynomial? So therefore the question, so it's f of z, an entire function such that for every z there exists a non-negative integer k which may depend on z, such that if you look at that order derivative at that point, you get that? Here one fixed derivative vanishes at all the points. Now all I know is I do some experiment, I find that at every point some derivative vanishes. Is f a polynomial? Is f still a polynomial? Okay. This is a slightly tricky question now, different. Okay. Turns out yes, the answer is still yes. What is that? How do I know there is a maximum? The number of points is infinity. Okay, so the maximum, there is nothing like a maximum. It could, you have to say that there is some maximum which works. That's the question, whether there will be a maximum. Okay. Number of points, I get maximum. Once there are infinite number of points in the complex plane, I don't know what is meant by maximum. Maybe at this point first order, at this point second order, at this point third order, then I am in trouble. So therefore, somehow this from this fact, and using the fact that it is an entire function and that we are working in complex, so all have to be put together and then get. And Bayes' theorem does it. Okay. Bayes' category theorem really does it. It's a very interesting thing. From nowhere, the Bayes' category theorem pulls up and say, look, I mean, don't worry about the same. You just check whether some derivative vanishes, then you will know the same derivative vanishes. So what I am going to do is looking at his basic idea that somehow I want to get hold of one derivative which vanishes. Okay, the maximum, that somehow the maximum idea has to be brought. So what I do is, I don't care, I collect all the points, the 0th order vanishes, all those points where the function vanishes. Then I collect all the points where the first derivative vanishes. Collect all the points where second derivative vanishes. So let an be the set of all those points such that the nth derivative vanishes. Okay, n equal to 0, 1, 2. When I say 0th order, that means the function itself vanishes. Now I consider the union of an. Okay. What can I say about this union? All of C, because at every point some derivative will vanish, so it will belong to one of the ANs. So this is equal to C, the entire complex plane. Because for every Z there must be one N where it must vanish. So therefore it will, every Z at least one AN. Okay. So therefore it is the union of all the ANs is C. Now C is a complete metric space. complete metric space. If it is a complete metric space, it cannot be expressed as a countable union of nowhere dense. So one of them must be not nowhere dense. Okay. So therefore C is complete. See how they use the power now. The completeness power is used first, and therefore by Bayer's category theorem, one of the AN is not nowhere dense. There the Bayer's is over. Now we have to go on interpreting the fact that it is not nowhere dense. Okay. So this is the theorem which shows the power of complex analysis, topology, all these things, how they join together and give us very nice results. Okay. So what say AN? Say AN is not nowhere dense. Okay. Now I am going to interpret the fact that A is not nowhere dense. What is meant by nowhere dense? I said that one way of interpreting nowhere dense is the interior of the closure is empty. Not nowhere dense means the closure must have at least one interior point. Okay. That means therefore the AN closure interior is not empty because it is not nowhere dense. Nowhere dense means it is equal to empty, means it is not this, which implies there exists an interior point of AN closure. Now look at those sets AN. The roots of the nth derivative. These are all the roots of the nth derivative, the points where the nth derivative vanished. This is of the nth derivative. Since this analytic derivative is all the zeros of a continuous function, the zeros of a continuous. So therefore, ANs are closed, so this is the same as AN. Okay, that I will leave it to you. AN are all closed. AN are closed. We will see that again later, being the zeros of a continuous function. What does it mean to say that there is an interior point of AN? There is a hole which is completely inside AN. So what it says is, in the complex plane there exists some disk such that is contained in, because it is an interior point. Because it is an interior point, a whole disk must be around that point which is completely contained in this. Okay. Now what does that mean? Since all these points belong to AN, the nth derivative must vanish at all these points. Okay. So therefore, Fnz is equal to 0 for all z in B or Z naught. Right? That means at least in ball it is a polynomial. Right? Because all the nth now a fixed derivative vanishes at all these points, and therefore it is a polynomial inside that ball. But if it is an entire function equal to a polynomial in some domain, it must be a polynomial. That is the power of the analytic functions. If it coincides with a polynomial in a small disk, it must be a polynomial everywhere. That is what is known as the analytic continuation property. Okay. So this is a very powerful theorem. Okay. Therefore, Fz is a polynomial in B or Z naught, and therefore since it is entire, it must be a polynomial everywhere. And therefore a polynomial. fact, see, look at various properties that uses. It uses the fact that the zeros of a continuous function are closed. It uses the fact that C is complete. It uses the fact that a complete metric space cannot be union of nowhere dense sets. It uses the fact of an analytic function that whenever it is equal to another analytic function, then it must be same analytic function everywhere. Very sweeping usage of topological ideas of nowhere denseness and Bayes theorem, properties of continuous functions, properties of analytic functions, and properties of entire function. Now try to prove the same theorem in the real number setup. It is still true, but the proof is very hard because this power of analytic functions is lost. See here what I did was, the moment I knew that it was a polynomial in a disk, it is going to be a polynomial everywhere, but that is not going to be. So what will happen in the real line is that you will get that it is a polynomial in an interval, but it is a polynomial everywhere. So work is much harder, but it is still true. Even in the real number setup, this fact is true. The proof is easier. The proof is the same in the first step. Apply Bayes, define this, use, in that case R is complete. Now we are using C is complete. We are dealing with real, R is complete. So you will get one nowhere dense set, and instead of an open ball you will now get a interval in which it is polynomial. Now the real horror starts of the real line. In the real line, if some just, for example, I can have a function which is like this, the linear function, and then subsequently can do all kinds of funny things. You see? So it doesn't mean it's a polynomial. Again decide to do exponential. So all kinds of things it can do. So in real life, just because it's in a polynomial in a piece, it doesn't mean the same polynomial everywhere else. However, in the complex case, it's much. So from this step onwards, see this part, this last part will take much harder work in the real. For us, it's so somebody there was a. If you are clever, you will do it in a. You are pulling up the problem to the complex numbers and then solve it, and the complex number come down to the real numbers. There is a famous saying which says that the shortest path between two truths in a real system is through the complex plane. Okay. It's like that. So whenever you are given a problem on the real line, any polynomial on the real line can be thought of as a polynomial on the complex variable. First lift it up and then get the fact that it is a polynomial there and pull it down that it's a polynomial. So that's another way of going through. But if you want number proof, it's very hard from that stage onwards. What you should do is, let us say we are working in 0, 1 or R, okay. Then what you will do, you will get one open interval in which it will be a polynomial. That disk will be replaced by this. Now you have got to work with these two pieces. Now in each one of these, because the closed bounded set is a complete metric space, you will get a polynomial. So like that you will get a number of pieces of open intervals. In each one of it may be a different polynomial. Now somehow you have got to patch them all and get one polynomial. That part is the hard part, which is again like a Cantor type argument. Okay, so there will be a Cantor like argument that comes into the picture. So this is not a, the Bayes category theorem has some very phenomenal applications. You will see a number of applications in functional analysis itself. The important thing is a complete metric space cannot be built by sparse sets of the type nowhere dense set. So these are common sense ideas, but they are finally take their mathematical shape. Okay. So this completes the basics of sets that we are dealing with in a metric space, and we will specialize over special types of metric spaces where the metrics are derived from a norm, or the metrics are derived from an inner product, and we will make the structure algebra also come into the picture, namely the vector space structure. So now we will bring in the vector space structure, we will bring in the metric structure and make them interact. Okay. So when they interact, there is good news, and there is a lot of flowers that blossom in that, and that is what functional analysis is. Okay. So basically, therefore, if a person is doing only algebra, he is not seeing the geometry. Topology is like geometry, neighborhoods, walls, open spheres, and things like that. Okay. So he is not seeing the geometry. But a person, if he is doing topology, he is not bringing the vector space structure and all these things. He is not seeing algebra. Okay. The analyst is one who makes the marriage between topology and algebra, and then one of the big thing that evolves out of it is the subject of functional analysis. The functional analysis is a subject that evolves out of the marriage of algebra and topology. Okay. An algebraist, a pure algebraist may not like to marry topology. A pure topologist may not like to marry algebra, but analyst is the one who says, I don't care, I will bring in algebraists, I will bring in topologists to my house, I will interact with them and I will get results. If they want to use it, they don't want to use it because they are strict algebraists, that is their problem. My problem is solved because now if I can use both these ideas, I got many things going through. So it is therefore, while it is good to be very rigid, it is not, you will miss many things if you are very rigid. You got to be open. Okay, if there is a problem, the question is, do you want to solve it only algebraically, or do you want to solve it topologically? Or you want to solve it only numerically, or you say, I want to solve it. What the hell, whatever comes in my way, I will use it. I want to solve the problem. So the problem solved is there. This is not very rigid about algebra or topology or anything. Anything that works solving the problem, solve. So therefore, mix algebra and mix topology and mix anything else that you can, you get results. Okay. So functional analysis therefore is the marriage of the notion of metrics over vector spaces. Okay. And when we do that, we get lots of nice things. Alright, so probably, though I said I will take the class on Thursday, this is probably the right place to stop. What I would try my best to do is, which told me that he would help, we would try to bring out some kind of lecture part, okay, within maybe before we next norm linear spaces, operators, functionals and so on and so forth, so that if refer to they enter the other sessions. Okay. So hopefully we can do it. Anybody who wants to pitch in and help Rohit, feel free to contact him. I think probably in touch with him. On passing. Shape. In the meantime, whatever he will